Hello and welcome to our 29th Virtual Research Café 10.0. I'm Frank Gomez, Executive Director of STEMnet here at the Chancellor's Office. Behind the scenes, we have Monica Alarcon and Jesus. Much thanks to both of them for working out the logistics and in publicizing today's event. The goal of the cafe is very basic, to share research collaborations across the CSU and perhaps to catalyze submissions of proposals later on. Everybody who's speaking are assistant professors, and it's a relaxed setting, each of them for 10 minutes, reason for why we call it 10.0. We hope you'll find some interesting presentations here and perhaps lead to a collaboration. Feel free to contact any presenter in the chat box when they're not presenting. At the end of all three presentations, we'll all come together for a Q&A session. I'll be monitoring the chat box for questions from the audience. So let's begin. Once again, we have three great speakers to present a snapshot of their work. Our first speaker is Alanna Cooney from the Department of Mechanical Engineering at San Francisco State. Alanna, the floor is yours.
Sorry, I'm muted. Thank you so much. There we go. So yeah, thank you. I'm very happy to be here and talk a little bit about my research. So my research, I'm an assistant professor in the mechanical engineering department here at San Francisco State. And I focus my research on thermal energy storage and other phase change heat transfer processes. And I also try to leverage machine learning methods in my work. So first, a little bit about me. So after I graduated from undergrad, I actually worked in industry for about 4 years doing heating, ventilation, and air conditioning design in mission critical systems, so data centers and electronic trading floors. And so after those 4 years, I went back to school to see if I wanted to pursue research and teaching. And so I did my master's at Marquette University doing research on heterogeneous combustion, looking at the different fuel components in liquid fuels and how those affect combustion properties. Then I came out to the Bay Area where I did my PhD at UC Berkeley in the Energy and Multi-Phase Transport Laboratory. And so a lot of my work looked at phase change interfaces, and that's where I started my work in thermal energy storage. Then I briefly worked this past spring and summer as a lecturer at UC Berkeley, teaching classes like experimentation and measurements and thermodynamics. And then that brought me here to San Francisco State this past August as an assistant professor. So very new, kind of just getting started in my research, but very happy to come here and find potential collaborators. So my work focuses on energy storage. So first we want to look at why do we need energy storage? So when we talk about decarbonization, it's not just as simple as moving away from carbon-based energy sources to renewable energy sources. And one of the problems is that renewable energy isn't always available when we need it. And so that's why it's really, really important that we develop energy storage technologies. And so this is a projection of the electricity generation in the year 2050. And so you can see here, this is the electrical load. And so it's projected that during the middle of the day, we're going to have this excess amount of energy being generated that we'll have to store so that we can use that in peak loads in the evenings when everybody goes home and cooks dinner and things like that. And so there's different types of energy storage. Batteries, we're all familiar, they're in electric cars. A lot of home photovoltaic systems have lithium-ion batteries where you can store energy. We also have chemical storage. That's things like combusting fuels, green fuels like ammonia and hydrogen. And then my work focuses on thermal energy storage, which can either be hot storage, where you store energy as heat, or cold storage, where you store energy essentially in the absence of heat. And so all these different types of storage kind of have their pros and cons. Electrical batteries are definitely the most dense in terms of, density of the energy storage, but there's also challenges. There's a lot of conversations about, are we going to run out of lithium at some point and things like that. So all of these have their pros and cons, but the reality is that we're going to need some combination of all these types of energy storage for the future, for the amount of energy storage that we're going to need. And so there's actually two different types of thermal energy storage. The first one is called sensible, which is where we store energy in a change in temperature. And so this is what goes on in the water tank in your home, the hot water tank, where, during the day, if you have a solar hot water heater, you can heat up that water. And then at nighttime, you use that hot water to shower. So you're just changing the temperature of the water. We also have latent thermal energy storage, which is where we have energy stored in a phase change. And so this is like if you go camping, you make ice, you put ice in your cooler, and then that phase change as the ice melts is absorbing energy. And so latent processes tend to be more energy dense, right? That's why we put ice in our coolers and not just cold water, because there's more energy that can be absorbed by that phase change process. And so because of that energy density, my work focuses on the latent thermal energy storage. And so what this looks like is that we have what's called a phase change material that undergoes a liquid to solid phase transition. And so in Europe, they actually have these to replace the hot water tanks in their homes. So this is essentially a box of a paraffin wax or a salt hydrate, and you have a heat exchanger. And so during the day, you could melt that wax to store energy using excess solar energy. And then at night, you have cold water that comes in, it freezes the wax to extract that energy, and then you get hot water to your shower. And so the advantage of these systems is that the phase change materials are typically non-toxic and widely available, unlike lithium-ion technologies where there's a lot of concerns with mining all of those resources. But there are some limitations, and so there is a lot of opportunity to improve how we design these latent thermal energy storage systems in order to increase the efficiency and also the rates that we can pull energy out of that phase change material. And so two common applications of latent thermal energy storage are concentrated solar power plants, where you have mirrors focused on a working fluid, heating up that working fluid to run a steam power plant, or building heating, ventilation, and air conditioning systems. So you could store thermal energy during the day to either heat or cool your building at nighttime. And so a lot of my work focuses on the concept of exergy, which is not just a misspelling of the word energy. So the way that Exergy works is if we think about these two systems, where in this first system, we have a cup of hot water at 200 degrees Fahrenheit and a pool at 70 degrees Fahrenheit. Then if we poured that cup of hot water into the pool and mixed all that water together, we'd now just have a pool at 70.5 degrees Fahrenheit. And so if we think about these two different systems, right, if we draw a boundary around these systems, no energy has entered or left the system. And so we can conclude that both these systems have the same quantity of energy, so the same amount. But if you think about, okay, you want to make a cup of hot tea, which system do you want to use? System one is going to be more useful for making a cup of hot tea than system two, because system two, we'd have to put more energy back into the system to heat up that water to 200 degrees to make that cup of hot tea. So what we can conclude is that system one has a higher quality of energy because it's more useful to us. We can do more with it. And so that's called exergy. So exergy is a measure of the quality of energy, not just the quantity that we have. And so the main conclusion here is that energy has both a quantity and a quality. And so this is important in my research because instead of looking at energy conservation from a standpoint of conserving the quantity of energy, I look at how we can conserve the quality of our energy. And so at kind of a big picture, what that looks like is this is a flow chart of how all of the energy flows through our energy systems. So here on the left, we have all of the sources of energy, and on the right, we have kind of the end use of energy. And so anything that we put into our energy system, so if we total all these numbers on the left, equals all of the, if we total the numbers on the right, because energy is conserved. So whatever we put in, we also get out. And so if we think about conservation of energy in terms of the quantity of energy, that would look like things like, driving our cars less so that we use less petroleum, which gets refined to gasoline that goes into our transportation systems. Or we don't turn our heat on quite as often, so we use less natural gas. So that's conserving the quantity of energy. When we want to conserve the quality of energy, that's actually looking at these end uses here. So you can see actually only about a third of the energy that we put into our energy systems ends up being used as useful energy or useful work. About 2/3 of that energy just gets rejected as waste energy. And most often that's going to be waste heat. And so of all this energy we're putting into our energy systems, we're only using about a third. And so when I talk about conserving the quality of energy, I'm looking at reducing this amount of rejected energy and trying to recapture a lot of that to make it useful. And so in my most recent project, I looked at developing a new type of latent thermal energy storage. So in literature, it's been shown that I showed that kind of one box of wax that you can use to heat and cool your water for your shower. You can cascade multiple phase change materials that melt at different temperatures to increase the performance and the efficiency of your thermal energy storage. But these systems are very static. They're very difficult to control. And so what I've developed is essentially creating a more flexible array of thermal energy storage modules. Each module can have a different type of heat exchanger, a different storage capacity, and it can have a different storage temperature. And then here we have 14 on-off valves. And so we can open and close those valves to essentially get 2 to the 14th different flow paths through this system. And so it allows for the opportunity to for optimization in how we control this thermal energy storage. And so essentially what I developed is a multi-objective optimization to control, to pick what the best flow path through this system is. And that multi-objective optimization has 2 objectives. So the first is to match a desired outlet temperature. So typically you want to have some sort of set outlet temperature from your thermal storage. And the second one is to minimize the exergy that gets destroyed. And so that's essentially minimizing how much of that quality of our energy is getting degraded during this energy extraction process. And so because this is a pretty kind of complex system with all of these valves opening and closing, it also lends itself really well to machine learning. And so essentially what I've shown is that I can train a neural network to predict, based on the operating conditions of my thermal energy storage, it can predict what valves to open and close in the system to make the system optimize, to make the system operate in the most optimized way. So essentially what I've shown is that my system here, it can match a target outlet temperature. So ideally you'd want a slope of 1 here. And so it does really well at matching a target outlet temperature. And this is the rate of exergy destruction. So it has a really, really low rate of degrading that quality of energy. And that's compared to baseline systems, which can pretty much just optimize for one or the other. So this baseline system can optimize for temperature, but not for exergy. And this one can optimize for exergy, but not for temperature. And so it's essentially just gives a more flexible way and leverages machine learning in order to be able to operate most optimally. And then I'll skip that and kind of go into my future work since I'm running out of time. So the future work that I want to work on is essentially right now, a lot of my work is focused on models, but some of the experiments that I've done have shown there's a lot of transience in these phase change processes. And so I want to do some experimental characterization of these phase change processes and try to see if we can use machine learning tools to predict how these thermal energy storage systems are going to perform. And then also use feedback from that experimental system to essentially retrain the neural network in real time for a real system that's operating to see if the system can figure out itself how to optimize. Another future project that I have is that there's something unique in the neural network that I've been developing in that the actual performance characteristics are the temperature output and the exergy destruction. And those are kind of separate from the binary outputs of this multi-label classification. So typically, in machine learning, if you want to predict, does this image contain a dog, a cat, or a mouse, right? In this picture, it accurately predicted the dog. It inaccurately said there was a cat in the picture, and it accurately said there was not a mouse. But here we don't really care if it inaccurately predicted a cat or if it inaccurately predicted a mouse. Those are both equally wrong. Whereas in my system, accidentally opening this valve when it's supposed to be closed might be more detrimental to the performance of the system than accidentally opening this valve when it's supposed to be closed. And so there's this kind of gap between the loss function of just predicting the correct valve and what the actual performance of the system is. So developing new training approaches to kind of rectify that situation. And then my last project, this is an area that I want to kind of expand into, is the area of energy justice. And so looking at, access to new energy technologies and how new technologies like thermal storage can be used to reduce energy burdens in different communities. And so I'd love to collaborate with people who, are working in, maybe the more policy side of this field to see how we could collaborate on those projects. And with that, I will pass it over to the next professor or the next presenter. But thank you so much.
Thank you, Alanna. Our next speaker is Lijiao Hu from Chico State. Lijiao.
Hello, everyone. My name is Lijiao Hu. I'm very happy to be here, and thanks everyone for coming. So a little bit about myself. I'm in the College of Agriculture at Chico State, and I joined Chico State last year in August. And since I joined Chico State, I have been teaching a couple of classes, including agribusiness management, computer application in agriculture, farm accounting, or food and hunger issues. And in terms of my research, most of my research focused on food safety. So I had one project related to how consumer responds to a food safety incident. And then I had a lot of projects related to private food safety certification market. And also had a project about organic certification, about how people are choosing different certifiers. And last one, I'm starting a new project related to non-GMO certification. So if anyone is interested in any of the topics or related topics, please reach out. I'll be happy to discuss potential collaborations. So today I would like to present a project related to private food safety certification market. So for this study, I look into whether private food safety certification really help improve the food safety system in the United States. So I'm using the US meat, poultry, and egg industry as one example. So private food safety certification it's called private standard because those standards are set by private entities, for example, private organizations or private retailers. So it started in the late 1990s by European retailers. At that time, they really wanted to have a higher food safety standard and impose it on all of their suppliers. So that's how it got started. And from the beginning, private standards have been business-to-business standards. So we consumers, we do not see a label for private certification on any products. So from the late 1990s to now, the private certification market has definitely expanded. And right now in the global market, there are 7 internationally recognized standards, including Global GAP. So this is the first private standards, and also is the most popular standards in the global market. And also we have FSC 22000, BRC, which is a British-based standard, and also we have Primus GFS, ISO 22000, and FS, which is a Germany-based standard, and lastly that we have SQF. So most of the standards are European-based or created in European countries, but we do have Primus GFS and also SQF being US-based standards. And I have some data on all of this on the 7 standards. So those are the number of certified producers or manufacturers in the United States or in the global market. So I highlighted 2 numbers for the US data. So in the United States, the popular certifications are are Primus GFS and SQF, because those two are mostly US based and they have a headquarters in the United States. But in the global market, Global Gap, it definitely has the larger share, and also followed by ISO 22000. So that is the background for private certification. And for this study, my objective is to see whether private food certification really help improve food safety. So the first part, we have been collecting private food safety certification data since 2015. So we're going to use that data and then merge the data with food safety data. So what we use as a measurement for food safety is from US DAFS laboratory sampling data. So this is the first study that we know that combine private data together with USDA, the government data. So USDA FSS, they conduct regular testing on all of the meat, poultry, and egg industries, and they test 5 pathogens on different types of products. So the 5 pathogens include E. coli, Salmonella, Listeria, Campylobacter, and Nano 157 stacks. And so our data is from 2015 to 2018. And I have the overall positive rate listed right here. So for E. coli, Listeria, and Nano 157 stacks, so the positive rate for the 3 pathogens are really low, is below 1%, which is great from a food safety and consumers perspective, but it does cause issue when we do the data analysis, which I will mention later when we got to the methodology part. So our model is very straightforward. We have the test results as the dependent variable. So if it's tested positive, then it's 1. If it's negative, then 0. So it's a dummy variable. And then the 3 key dependent variables we have, whether the site is certified with BRC, SQF, or FSC 22000, these 3 certifications. So our 3 key independent variables are dummy variables as well. And also we include other independent variable and control variable in our models. So it's a very simple model. We have test result equals to the certification status for BRC, SQF, and FSC. And earlier I said that the test results are going to have a lot of zeros because most of the pathogens have very low positive rate. And then on the right-hand side, for the independent variable, we have a lot of zeros as well. So it creates 2 issues in our methodology. One, so there are rare event and separation issues. So what happens when we run a regular or standard OLS is most of the observation do not enter the regression because most of them are 0 values, and it will cause a biased estimation. So what we have to do for this analysis is we had to adopt a penalized maximum likelihood method or a first method. So eventually this model allows us really force all of the observation into the regression. So this is our regression results. So I'm showing you guys the regression results for the first method. So we have 5 pathogens and the 3 key variables. So what we found for this analysis is we do find that BRC actually are negatively associated with Salmonella and Campylobacter test result. And SQF is negatively associated with Campylobacter and Listeria test results. So FSC 22000 is not significant for all of the pathogens, and that's expected because FSC is really not a major certifier in the United States. So the conclusion that we have for this model is that we do have mixed findings for different certifications, different standards. For adoption of BRC certification, it does help improve the Salmonella and Campylobacter test result, and adopting SQF will help improve the performance in Campylobacter and Listeria test result. But we do not find any significant result for FSC and other pathogen test result. So that is a conclusion for this study. And then lastly, I have my contact, my email information right here. So if you guys have any questions or comments, feel free to send me an email. Thank you.
Thank you, Lijiao. Very interesting presentation. Our next speaker is also from SF State, Eileen Gonzalez from the Department of Physics and Astronomy.
Okay. Okay. All right, so I'm going to talk about my work, which is very different, and it's on characterizing the atmospheres of brown dwarfs and directly imaged exoplanets. So a little bit about me first. I grew up in Virginia Beach, Virginia on the East Coast. I went to Michigan State for my bachelor's in astrophysics. I actually came out to San Francisco State for my master's. After my master's, I moved back to the East Coast and went to the City University of New York Graduate Center, where I worked with the Brown Dwarf in New York City Research Group. And I spent the majority of my time at the American Museum of Natural History. From there, I moved to Cornell to start my postdoc as a 51 Peg B fellow. And I just came back to San Francisco State this fall to start as an assistant professor. And then some things about me that's not related to academia. I have an incredibly large collection of plants that made this cross-country move with me. There's about 50 of them. And I am also a swing dancer, and I actually had started that when I was out in the Bay Area as a grad student. And so my work is on understanding the pathway to habitable worlds. So eventually the big goal for exoplanet science is to image an Earth-like planet. We're not there yet. And so what I work on is trying to build the techniques for being able to characterize the atmospheres of these planets when we can get down to imaging them. So I currently work on exploring the atmospheres of brown dwarfs and directly imaged exoplanets. So brown dwarfs are objects that are about the same size as Jupiter, but they're more massive. They have temperatures ranging from about 250 to 3000 Kelvin. And they're all roughly the same size as Jupiter. So understanding their atmospheres along with those of directly imaged exoplanets, which are just exoplanets that are about the same size as Jupiter and further away from their host stars, we can really try to understand a lot about what's going on. So understanding their thermal profile, so how their atmospheres are behaving in pressure versus temperature space, getting at their chemical composition, understanding their metallicities, looking at cloud and haze properties, and taking all of that and tying it into really trying to understand how these planets formed and evolved. And so as we increase our observational tools and work on our theoretical techniques, through time, we'll start to be able to image smaller and smaller planets, and we'll eventually get to imaging Earth-like planets. So the goal is to have this technique really well pinned down so that we understand what sorts of difficulties we'll come into. And so because brown dwarfs are very cold and cool, they have lots of clouds and gases in their atmosphere. So here, as you move down, you're moving to deeper, hotter, and denser layers. And you can see that they are composed of a wide range of clouds and gases. We primarily are seeing silicate clouds, iron, corundum in some of these hottest objects, which are off to the right. And as we move to the cooler brown dwarfs, we're starting to see them being dominated by ammonia, water ice clouds, and methane. And so for my work to really dig into understanding their atmospheres, I use a technique called atmospheric retrievals. And so an atmospheric retrieval is a theoretical inverse spectral modeling technique that makes minimal assumptions about the physics involved. And so that's a really big sentence, so we'll break this down. So you can think about modeling on two ends of a spectrum. On one end, we have self-consistent grid models where we try to put in as much physics and chemistry. We iterate down through that model and we come out with a model spectrum that we can then compare to our data. We also get out parameters such as the temperature, the surface gravity, the radius, etc. on these objects. from our model. And when we try to fit to our data, we only have a few knobs we can turn to make a resultant spectrum to try to fit to the data. And typically, because of that, we struggle to fit all of the features that we see. On the complete other end is what we have for free retrievals or atmospheric retrievals. You try to put in as smallest amount of physics and chemistry that you can, allowing for many, many knobs that you can turn to try to fit your data. And because you have so many knobs, you can tend to produce a model spectra that fits your data much better. And you can kind of see from both of these ends, the retrieval models can feed back into the models that include all of the physics and chemistry to kind of see what things we might be missing from our models. So how brown dwarf retrievals are actually relatively new, because we've been using the self-consistent grid models in our field for quite a long time. So how do these retrievals actually work? So we take a spectrum of our object, and based on that spectrum, we can come up with a list of gases that we expect to find in the atmosphere. And then we have to do some setups for our model. So how we want to parameterize our thermal profile, or how the atmosphere is behaving in pressure temperature space. If we think we have a cloud in our atmosphere, we want to include that into our model. And then how do we want to treat our chemistry? Do we want to get out values for each and every gas we put in our model? Or do we want to make an assumption that's in equilibrium and pull out values based on that? And then lastly, there's some underlying assumptions that we don't change in between each of our models, and that's our radiative transfer treatment, and then where we're getting our abundances for these gases. And so we put all of this into our model and we explore it in parameter space using a Markov chain Monte Carlo or nested sampling. So how the sampler works is we're taking our data and we're just trying to fit it to a model. So as you saw, we have many, many parameters in our model, but we're just focused on two. Here we have water and CO. So we fit our model to our data. We say, great, that looks good. We'll take a step in parameter space. We'll try another model. That doesn't look so great. And we keep doing this hundreds of thousands, even millions of times, until we find regions where we're likely to find our best fitting models versus where we're going to find poor fitting models. And then we take that and translate it into getting parameter values for our models. So on the x-axis, we're looking at our abundance of CO, and the y-axis is really the probability of getting that value. So where we find our good fitting models, we can find the peak of our distribution to get our value, and then our uncertainties. And we can do the same for water and all of the other parameters in our model. And so what comes out is abundances for each of the gases we put in our model, a thermal profile to characterize how the atmosphere is behaving, cloud properties if we include a cloud in our model, and then we have our retrieved spectrum, which we can fit to our data. And because of this flexibility, we tend to get a retrieved spectrum that fits much better than those models that try to put in all the physics and chemistry at once. And so the primary thing I'm focusing on a variety of my projects is trying to probe the formation and evolution of these objects. And so a good way to do that is to use binary systems. The idea is to try to probe their carbon to oxygen ratio, because we can use that as a formation history and evolutionary tracer. And so if these objects form together, they should have a similar carbon to oxygen ratio. And so for this pair that I have worked on in the past, these are two widely separated dwarfs of different spectral types. We found that their C to O ratio and metallicity point towards them forming and evolving together. And it's great that we can get this out of a single system, but to really understand these on a population level, we need to probe large samples. And traditionally, from using the retrieval method, we find for our colder brown dwarfs that their C to O ratios are much larger than stars. And we're questioning, why is this happening? So one project I'm working on right now is to take brown dwarfs that are in pairs with higher mass stars, where we can really constrain their abundances to get their C to O ratios. And benchmark that to the brown dwarfs. And so interpreting what's coming out of these models is what I would love to have collaborations about. And so this is a project I'm working on with some JWST data that's coming down in the near future. Making these interpretations are complicated. The C to O ratio can tell you where in the disk this object formed, but it's also tied to the metallicity. So on the left-hand side, you can see C to O ratios at different temperatures, and it's going to change depending on the metallicity. So it's kind of a feedback loop where if you really want to get at the C to O ratio, you need to understand the metallicity, which ties into all of this. Additionally, for these objects, they have, the warmer ones have clouds. So here I'm showing a silicate feature that you can see between 8 to 10 micron. We think these can be a wide composition of clouds. Typically, we found them to be enstatite and fosterite, but depending on the C to O ratio, that can also change your magnesium to silicon ratio, impacting what kinds of clouds can form. So trying to understand where we might be losing oxygen compared to carbon is collaboration I would love to have. So here I'm just showing different kinds of clouds that can form based on your fractions of magnesium or silicon. And then lastly, with the new JBST data, we're starting to dig into these cooler objects, and we traditionally haven't had lots of spectra of them. So we're starting to observe things that are not expected. So on the right-hand side, I'm showing data in black versus a model in red, and trying to interpret why we're seeing things that we don't expect, what kinds of chemistry can be going on in the atmosphere is what I'd love collaborations with. So thinking about people who work on atmospheres or chemistry, or even geologists have been people I've been collaborating with. And lastly, I'll just throw up that I am also doing an outreach project, Black in Physics. We are a 501(c) organization. We're a very small group of people. There is 4 of us that are trying to promote work for Black physicists and astronomers. So if that is something you are also interested in collaborating on, I am happy to have people help out. We typically do a week called Black in Physics Week every year, and we're working on making some changes to that for the upcoming year. And I will leave it.
Great. Thank you, Eileen. And thanks to everybody for your presentations. And now I open it up for Q&A amongst everyone who's here. Any questions for anybody? And this goes for the speakers too, if they want to ask questions of themselves. Yazdan, I saw you had a couple questions for Alanna there. I sent them to her. You may want to reiterate a couple of them.
Thank you. I have sent email to her, text to her. She has responded to some of them. But, you know, one of the things that I will repeat here will be something. Is she interested in constructal law? Because, you know, the thing that she was mentioning, it is a little bit in that direction. So this is my first question. And then what was the exergetic efficiency of the study that she made? That's it.
Yeah, so we so for the constructal law, thank you very much for those resources you sent. I think it'll definitely pair very nicely with my work, just because we're focused on that, minimizing the Exergy destruction. In terms of Exergy efficiency, we didn't calculate it because in our first paper, we essentially just looked at the energy extraction. And so we didn't really calculate, like, for a full cycle what the Exergy efficiency for the system was. We just looked at essentially the loss function of which was the ratio of Exergy destroyed to energy transferred, to make sure that this array could match the performance of a typical cascaded system. And so kind of in the next iteration, we're going to look at the full charging and discharging cycle to see what those Exergy efficiencies would be.
Thank you.
Yeah.
Louise.
Hi, my name is Louise Edwards. I'm a professor at Cal Poly San Luis Obispo. Thanks everybody for your wonderful and clear presentations. I'm an astronomer and not a not a planet person, so I learned a lot. Eileen, my question is for you. You started out, you know, talking about this goal of being able to image an exoplanet. which will be so exciting. And then how, and then went through this wonderful story plan of how, you're predicting the different chemical compositions in right now brown dwarfs and eventually working towards the kind of Earth-like exoplanets that we want to eventually image. And I'm wondering if you could circle it back to that. So understanding in this great depth all the chemistry and the spectral energy distributions and everything, what does that then tell us when we get that image of that Earth-like exoplanet? Like, are we expecting some colors, or the planets on the way to getting to Earth-like? Is knowing, I guess, knowing the underlying chemistry for an image, how do we translate that best? Is it usually the colors?
So for the directly imaged planets, because they're far enough away from their star, we don't have to infer that they're there like we do for transiting planets. So we have spectra of those objects themselves, so we can look at them directly and try to determine their composition. For the Earth-like planets right now, we're only detecting them through indirect methods. So we have to account for what's going on in their host star. So things like stellar variability can show up in the spectrum that can really change your interpretation of what's going on in their atmosphere. So really, it's more of trying to build on this technique and thinking about what sorts of things you're going to encounter as you move to different size objects, different data quality. With the transiting exoplanets, people are doing retrievals on them, but they're probing a different region of the atmosphere. They're getting much smaller differentials in pressure, so they're not seeing all the way down. They're accounting for stellar variability, but we're finding things like looking into the clouds, depending on how good our data resolution is, we can get much more information on the kinds of compositions. With lower resolution data, you can kind of go between saying cloud or no cloud. When you have higher resolution data, you can start saying particularly what kinds of clouds you expect to be in the atmosphere. And then that can help drive kind of understanding, well, if this kind of cloud is forming, that's pulling out oxygen, we're going to have our atmospheric C/O ratio, but we really want to get at the bulk C/O ratio to understand what was there when it formed in itself.
Yeah, okay. So the method that you're doing, the hope is that it will really be able to be used beyond brown dwarfs, like eventually more Earth and Earth. Yeah, that's fantastic. Thanks.
So Lijiao, I saw that salmonella had about 5%. So does that mean if one boils it down that approximately, and maybe this is not my best scientific way of looking at this, that 1 out of 20 eggs have some remnants of salmonella in them?
Actually, the numbers should be much lower because when they are doing the testing, they're not only testing the product, they're testing everywhere on the site. So that might include somewhere actually outside of your production. So what USDA will do is if they so salmonella is not, so if they test for E. coli, that's an emergency. They're gonna cease the production immediately. But for salmonella, it's more common, and also if it has to be a pattern for the USDA to stop your production. So whenever they're testing for certain pathogen, they're gonna do follow-up test. And if they for salmonella, I think if you have positive tests for more than 3 times, they're gonna stop your production immediately. So 5%, it does not really mean that for every 100 that you have 5 that has salmonella on it. So that sampling can from anywhere, but what USDA posted online, we have no information on exactly whether it's from a product or it's just from a service nearby. So that's the information we don't have access to.
Thank you. I guess it'd be good to know what the, is that kind of just information they don't want to provide information on? I mean, why is that such a industry held secret?
Yeah, it's the information they're not disclosing on the website, but from the way that they're describing the inspection procedure, I'm guessing all of the numbers, the percentage of all of the positives should be lower than what they're posting on the website.
Okay, great. Thank you. So Alanna, I do have another question. So what is this, all this lithium deposit that was found in the Nevada-Oregon border region? Do you have any comments on that?
So I don't deal too much with the like electrical batteries. But it is definitely kind of one of the main concerns. When you look at the different types of energy storage, there's a reason why batteries are everywhere. They're very energy dense, so you can store a lot of energy in very small space. When you talk about thermal energy storage for, a concentrated solar power plant, you're looking at buildings of energy storage. So it's very, very large because the thermal energy storage just isn't as dense. But with the batteries, there is all of this concern. If you look at the ethical practices of where all of these resources are mined, you can even look at a lot of the mining practices are also very energy intensive. So how much energy are we expending to get the resources to make these batteries to then be, energy efficient? And so that's why, my argument is I really think we need a mix of all these different types of energy storage, because they do all have kind of their pros and cons and their limitations where, it's not going to just be all batteries in the future or all thermal energy storage. There has to be kind of a balance so we're not depleting a lot of our resources.
Okay.
Yeah.
And you also did show a slide about latent thermal energy storage. I guess there was a box you showed from Europe and how it worked. So is one then more heavily limited to showering at night, because you showed that the showering occurred at night based on how the inputs and outputs are, or was that just there because more people shower at night?
Yeah, it's kind of there. The idea is that, during the daytime you have excess solar energy. So you could either use that, like directly to heat water to melt the wax, or you could use an electric resistance heater, or what kind of the future I think will probably look like is more heat pumps. So you would have a heat pump that could, heat your thermal storage. It could also heat your house. And so you would use that during the day when you have excess solar. And so then the storage would be for, at nighttime when that solar goes away, which is, typically most people are either showering in the evening or the morning when the sun isn't out. And another advantage of that too is I mentioned the latent storage is more energy dense than the sensible storage. So one of the ways that product is marketed in Europe is that it takes up half the space of the hot water tank that's in your garage, because that energy storage is more dense. So you can fit it in a little closet in your house and you don't have that huge tank anymore. So there's energy efficiency benefits, but there's also some practical benefits as
well. Okay, well, great. Well, I appreciate that. And some of my work is still in the area of microfluidic fuel cells and batteries. So, we're generating, small voltages to operate, small things like LEDs and watches and calculators and pregnancy tests. And so we're not generating more than a couple hundred milliamps and, 2 to 5 volts. So we're not going to operate a Tesla, but certainly, small types of devices. So I'm always interested in new types of energy devices, and certainly when issues of climate change, which is really all around us, there's that connection there also. So I appreciate your talk and really everyone's talk today. Once again, we're coming to an end again of our virtual cafe. Just FYI, we do have a webcast in a couple weeks on the NSF Career Awards, where we will highlight a number of different CSU awardees on November 1st. That's 11 o'clock on Wednesday. And we have a proposed next virtual cafe on Wednesday, November 15th at 11 o'clock. That being said, I hope you all have a good rest of your week. And at least down here, it's going to be a little warmer over the next couple days. Thank you, everybody, and have a good rest of your week. Take care, and also have a great weekend. Take care. Bye.
Thank you.
Thank you so much.
Thanks.